Good morning, ladies and gentlemen. Thank you very much, Paul, for such an interesting presentation before. So we have already first impression of the impact of flexibility on the plant overall for BWR. What we speak today is the overall impact of flexibility of various types and of various levels for both P and BWRs, but not from theoretical point of view, but from operational point of view. And this is also, so I will do the introduction on the flexible operation itself, and the vibration part will be presented by our expert on vibration measurements, Peter. And the team was quite strong from Framatome side. We had also people from Fatigue, from FIO, from eTechnic, and from Numeric as well. The next slide, please. Hello? Yeah, thank you. So these projects were supported by Energy Force vibration program, and the idea was to gather all available information on the impact from various interviews. So we were able to perform mostly 5 interviews, and these 5 interviews collected information from 1 and 2 and or sometimes even 3 different plants from German utilities. We spoke with all 3 utilities in Germany, and the focus was to identify the components and the types of vibrations they have seen over the last 20 years, and to look which kind of mitigation possibilities they had, or which other mitigation possibilities could exist for the future and could be transferred or applied for the Nordic plants as well. The next slide, please. Before we go further, we thought that the most important thing is to find a correlation between the type of the flexibility the plant is performing and the results we see. So the first of all, in all interviews we performed, we spoke about which kind of flexible operation the plant really performed over the years. And also we tried to understand if they have seen something, was it really linked to flexibility, and then for which type? And it was quite a hard task. So these pictures are showing the collection of overall information to show which kind of flexible operation exists in the plant and what are the levels the plant participating in over the years. And this table is done on basic of the services, grid services the plant is performing. So they have the frequency control, primary in 30 seconds, but in Germany already this one is carried out in as a step in 2 to 10% of rated electrical output. So it's sometimes could be even 150 megawatt step, which is very fast as well in 30 seconds is said. And the typical values which they're performing each day are much lower. They're at about plus minus 50 megawatt electric. Then we have frequency oscillation reserve, which is differentiated between automatic one, which is provided in 5 minutes. So we have about typical 50 megawatt electric, which they provide, and we have manual frequency restoration reserve up to 15 minutes, about 150 megawatt electric, typically plus minus. This is this is already so-called ramping service or ramping type, which is performed with a ramp rate from 10 to 30 megawatt per minute. Similar thing is the load following itself. So it's also the ramp and also the same as redispatch measures. So for the plant, it's not important who needs this. It's if it's come the request from the load manager or from the grid itself. In the end, it's only the ramp with the ramp rate, and it's the level where the plant is performing such kind of services. And typically, to summarize all we have seen, the plants are trying to perform all kind of services from 100 to 60 or 50% maximum, and they try to avoid long LPO, and they strongly try to avoid LPO and long LPO on the low levels. But still, what is LPO? It's an extended low power operation when it's not so important how fast you go to this level. but you stay quite a long time, more than 12 hours, 24 hours, low level. It's a planned type of maneuver, but typically it could be even till the minimum load of the plant. And we have such an example, which you will see later on illustrated, with a plant who performed a long time extended low power operation on mostly 40% of the load over about 2 months. And we tried to find out most interesting examples and to learn much more about vibration impact on them, to be able to transfer such information to others afterward. And it was in the end what the German plants have done themselves as well before they started the strong flexibility. The next slide, please. So I will go through some illustration to show how it looked like. This is one BWR showing the classical, typical flexible operation over 1 month. The most typical type of flex operation is going from 100 to 70%, 70, 80%. Sometimes, if it's needed, they go to 60%. So as was said by Paul before, they're trying not to use the control rods. So they want to stay in recirculation mode. And the durations, if you analyzed years of performing on flex operation, so the typical duration is from 1 to 3 days. Sometimes it's longer, but it's only single events. This is for the next plot. We looked if they are also participating on some secondary control issues, which are much faster. So we found one plant who performed it in a range of 100 megawatt electric. But after these automatic reserve, they also could be called to perform the classical load following, and they will do it also only till 60% of the load. The next slide, please. This is just to give a feeling of the 1 year operation. It's already another BWR. And these BWR was performing small frequency control of 22 megawatt electric, automatic frequency restoration reserve with minus 30 megawatt electric, and the MFFR with minus 90 megawatt electric. The ramps rates were between 10 and 15 megawatt electric per minute, and the load follow was performed with a similar ramp rate. And all the services, as you see on this 1 year picture, are going from 100 to about 60% of rated electrical output. I went to each month in detail and looked where the reduction coming from. Was it really load follow, or there were some maintenance issue or other issues? So to give an overall picture, so the duration of such a low level flexible operation or related reductions, they were typically between half a day and few days, and the longest time was about 4 days on such a level. The next slide. So now we make a step to PWO world, and this is for us very interesting example of the plant which is doing base load operation typically, but when they have a strong negative prices on the market, they go really low and they go mostly to the minimum load. So it is the blue curve, light blue curve, they really go to 30-40% and they stay there. Here we have about 12 hours or something like that, but sometimes also during the weekends. Next one. And this is the plant. We also had a very long and intensive interview. This is the plant with the highest flexibility in German grid. So they are performing remote controlled flexible operations. So they do everything the grid will need. And this is what you see on the right-hand side. It is 1 month. And during this 1 month, this red curve shows the changes of the power. And these changes are going in the range of about 600 megawatt, but they don't go lower. So only in extreme cases, they do go lower or stay longer. So they're really always changing with the requests. And they're typically, so this is 1 month, but the year looks very similar. So and this red curve is some overlapping of different type of services. They have primary, secondary control, 100 megawatt electric primary, IFFR with 150, MFFR with 300 megawatt electric, and load following. And the RAMs they perform were sometimes in the years about 40 megawatt electric even, and 30 megawatt electric, and now they went back to 20 megawatt electric per minute. So depends on what the grid required, how is the payment. So it's all optimization of the plant. So and we had very intensive feedbacks from them. And we collected not only vibration, but also looked a little bit right and left or some wear issues or fatigue things as well. Thank you. Next one. So, and this is for me the most interesting curve we had. So this is the PWR who performed really ALPO, but not only. So it performed strongest daily load following, daily, weekly, whatever, 2.5 years long. And after that, in the end, they had also mostly 2.5 months of LPO on less than 40 percent of reactor power. And if you look at the curve, it's reactor power over the time. They were 2.5 months or 2 months, mostly 30% of reactor power. And all information they had, and the plant was monitored in a very good way. So all information they get, they collected, they evaluated for mostly all components, and they tried to summarize the experience and to transfer these to other plants that didn't perform such extreme load follow or LPO part load operation. And we had a very interesting discussion with them. And now with this, I would like to move to Peter, that he can speak about the vibration impact. And he will start with a very important understanding of how the German plants monitor their components, because it will help to understand also what they see, because you have to know how you measure and what you measure to understand also the impacts which can be shown. Okay, thank you very much. Peter, the floor is yours.
Yeah, thank you, Tatiana. Good morning. This is Peter Forster from Framatome. I'm working in the field of vibration since 25 years now, and just recently also on the vibration measurement of our new EPRs commissioning in Taishan and in Finland. What I just want to show you on this slide is a short overview on the vibration monitoring in German PVRs and also BVRs. On the left side, you see a sketch of about nearly 40 vibration sensors, which are installed according to a German DIN standard. They are measuring vibration, displacement, pressure pulsations, neutron flux, and so on. In the middle, you see the monitoring or instrumentation of a loose part monitoring system, which is also according to a DIN standard. Additional about 20 acceleration or noise sensors are installed on a typical for-loop plant. And with this information, as the word is saying, loose part events can be detected, but also with some adjustments, vibration issues can be deeper analyzed. So that is worth mentioning here in our opinion. So about nearly 60 sensors are in general installed on the primary circuit in German plants. Here the standard is more related to the pressurized water reactors, but also on the right side, the BVRs are typically installed with sensors and from the loose part monitoring system. And there is possibly a detection of loose part, a mass estimation, but also some algorithms to avoid faulty alarms and filter them out. So in sum, a high density of sensors or information is gathered from this instrumentation. So on the next slide, please. I just see the slide number 9. Monica? Ah, okay. Now it's number 10. Yes, thank you. So already the results from our interview we have performed with, I think, nearly all operators in Germany and also in a Swiss operator. The information is a little shortened here in the tables, but I think quite interesting. The information is from about more than 12 plants which operated flexible operation already in the 90s and or are still doing it today due to the regenerative electrical generation. On the first table here is a summarization of a feedback coming from the nuclear island from PVRs and BVRs you see in the first column. And if we're talking on the first row, a lot of influence was seen in the PVRs on the pressurizer spray nozzles, which are facing thermal fatigue, which is vibration aging mechanism in the third column. The operator's observation see typically, that is meaning by this T, thermal transients alter this material and realized countermeasures in the fifth column were here in this way that the INC measures were implemented to spread the transient temperature loads on these nozzles. That means the fleeting nozzles were spread to others to decrease this thermal load. Lifetime impact on this pressurized spray nozzles was quite high in this way that the usage factor will be reached in 2023. That means after the planned shutdown of the plants in 2022. That means they would have to change these nozzles if they would run further than 2022. So possible mitigation measures in the last column, we see, or the operators see, that an online fatigue monitoring would help to ease the problem. So the second row is on both PVRs and PVRs. The recuperative heat exchanger is also facing thermal fatigue, which alters the material because of the increased in and out surges. A countermeasure, a realized countermeasure is operation of more trains during part load operation or flexible operation to spread the thermal loads on more trains. So the usage factor by this is already rising significantly, and also a fatigue monitoring is seen to better deal with this problem in the future. So the third row is dealing with the control rod drives. There is seen mechanical degradation of the drives themselves. The control rods have to move more often due to flexible operation, which is also typical for this mode. Realized countermeasures are calculative measures for the extension of the lifetime. And the impact of the lifetime is that the number of the design activations were already overstepped in some plants. There's typically 10 over the 6 activations, but with an more intense monitoring and inspections, they can run these control drives further. So the last row is on steam generators. There are vibration observed impacts by fluid that produces more noise in the steam generator, which sometimes come to alarms in the loose part monitoring system. But the realized countermeasure are more often inspection and monitoring. The effect, lifetime effect, is currently seen quite low. So a specific tracking by monitoring is performed on this steam generator item. So coming to the next slide, please. It would be slide 11. Monica? No, okay. So now these following slides are dealing with the turbine island issues. You see at the first row on both PVRs and BVRs that the operators mentioned oftenly motor-operated valve drives. The vibration action mechanism is activation due to the many load transients, and they saw mechanical degradation of gear parts or stems is very typical. Realized countermeasures are more often inspection and maintenance. Lifetime impact is high. Typically more than 20 times more of controls are observed on these operated valves, and an online monitoring is seen as a further mitigation measure. So the second row is on main steam regulation valves, where fluid activated vibration occur, especially at low load operations smaller than 40%. Very high vibration have been oftenly observed. The operator tried to avoid these load ranges, but the lifetime, or fortunately the lifetime impact is not seen very high in the moment, but it is monitored quite closely, and also vibration and fatigue monitoring are further possible mitigation measures. So the third row is on main feedwater pumps. There have been observed 4 structural vibrations in part load conditions quite often, and the operator tried to avoid these operation ranges or place or run more pumps for a special load range. So the lifetime impact was middle, and the vibration, mainly already installed vibration monitoring, is taken into consideration. So also a topic on main feedwater pumps in the last row, that cavitation occurred on the high pressure stages of the pump with loads lower than 50%, quite rarely. The operator tries to avoid this operation range and runs less pump in this range. So the lifetime impact is middle, and the noise monitoring is further mitigation measure. So please, the next slide. Yes, this is also dealing with turbine island items. On the first row, the low pressure turbines end stages are facing quite often erosion on the lower or the inner blade sections, coming from the backflow of the last 2 blade stages due to part flow conditions. That means there's a kind of circular flow within in the last turbine blade sections, and that means that on the back side of the blades they are observing erosion problems from the droplets. So inspection and also change of these blades have been performed. The lifetime impact is quite high, and possible mitigation measures is an inspection and avoidance of this low load operation. So the second row is with turbine shaft torsional vibration excitation. It is often observed on the grid, especially in the northern part of Germany, that a lot of peaks are coming to the generator from the outside, and this comes to torsional vibration excitation of the turbine shaft quite high. Mechanical and electrical monitoring have been made. On the other hand, but it's seen that the lifetime impact is not so high or seen as low in the moment, but the vibration and fatigue monitoring is still proceeded. So the third row is dealing with moisture separator preheater. There have been corrosion effects and on mechanical load effects. At part load conditions, there is a change of the pipe passivation due to chemistry because of the changing of the pH value in these part load conditions quite often. The countermeasures were already intense repair or exchange on the pipes of the heat exchanger pipes, and so the lifetime impact is quite high because mostly it's a chemical degradation. Large area are concerned. And the operator tried to avoid these part load conditions or change the pipe material are possible mitigation measures. So the last row, the preheaters in general are facing erosion due to flow to change flow conditions. Flow pressure and humidity will bring up these erosion problems. Regular inspection, but also cladding resistive material were already realized in the plants. Lifetime impact is so seen as more middle, and regular inspection and additional cladding are possible further mitigation measures. So on the next slide, 13. Yes, we see the last from the turbine island, the component, electrical components of the unit, auxiliary power supply. Some are facing mechanical degradation, which is quite rarely. More often inspection on these power conductors is performed. The lifetime impact is not so high due to these countermeasures, and monitoring of the gear, motor, and stem are further measures to recommend. On the main generator, the second row is also seen this torsional vibrations. The effect are a little different or specific that electrical and vibration measurements on the grid produces, and they saw already some degradation in the isolation material of the stator. So it is, one has to take an eye on it, in our opinion. Otherwise, due to mitigation measures, the lifetime effect is not so big. And but in the end, an empiric mathematic model can give alarms to the shift if these torsional vibrations coming from outside peaks are getting too high. So on the last row, the generator was also rarely faced with higher O2 content on the cooling water, which led to corrosion of copper tubes for the cooling. Was quite single occurrence. Maintenance activities have to be risen, and the lifetime impact was not so high due to countermeasures, and the mitigation measures are maintenance. So the last table on the next slide is dealing in the first row with the fuel in general, or the mechanism could be flow-induced vibration, but there was not seen any effect in the moment. So we think, or the operator thinks, the robust design and fretting resistive design of the fuel is the reason for this. Currently, there is no lifetime impact defined, and also no mitigation measures are not applicable at the end. The last point we saw is that in general, on various secondary circuit components, erosion and corrosions occur, which can have significant effects on these parts, but this was already present before these part load operations. That is a general item which have to be kept under observation. Realized countermeasures have been individual expert evaluations, so the lifetime impact is just not seen so high due to mitigation measures, and monitoring and software tools like COMSI can be help on this issue. So the next slide, please. Next slide, number 15. Yes, an example on these, we see a new approach of surveillance concept for the secondary side, which are typically less instrumented compared to the primary circuit. And there we made a test implementation in a Swiss power plant for dealing with the special load follow effects. That means we installed nearly 20 additional sensors on the moisture separators, preheaters 4 sensors on a big feedwater preheater, an additional 6 sensors on a low-pressure condensate pipe, which was vibrating very high. We have an additional wall cabinet. You see it in the right lower corner. It's quite a small cabinet installed in the machine in the turbine house. And which is quite important and useful, we made a parallel acquisition of more than 1,100 operational parameters from the processing system, which are already present in the plant and makes this combination with the vibration recording. You see in the left corner a small architecture on this with the sensors on the left side and the gathering of this information to a common system. In the middle, a photo of a quite simple installation of acceleration sensors on a component, the heat exchangers. And in the upper right corner, you see a small side effect. What you see here is not a vibration, it's more a level oscillation of a preheater, which a long period length of minutes. And with this parallel acquisition of more than 1,000 operational parameters, we could help the operator to get closer to this item. What was the reason for these upcoming oscillations? And because this led to an outflow into the condensator of this high pressure condensate, which was not useful or not wanted. So coming back to vibration on the next slide, there is an example of this vibrating high pressure condensate pipe. We made this here on the left side to typical installation of a 3-axis sensor installation on the pipe on a horizontal section, and also on the lower photo near the support. In the middle, you see the isometric view, and in the upper right corner, you see a waterfall spectrum. On the abscissa, on the lower part, you see the frequency, and going to the right corner, you see the time, and you see at approximately 3 Hertz, there's a latent natural frequency oscillation. And when the fluid comes to a beat or a pushing of the pipe, you get a high excitation in the region of 3 Hertz. That it's the natural frequency of this pipe, and you see this red mountain, which leads to high vibration levels that could be observed by this instrumentation. So the next slide gives some information on the analysis. Yes, on the left side, you see here a spectrum, and at 3 Hertz, that is the black pins, there is the lowest natural frequency with the vibrating of the pipe. The other frequencies show here more amplitude, but it is an acceleration spectrum. That means the displacement, which is normally leading the aging or the stress of the material, the higher frequency you have a less influence. So the main influence has this low frequency excitation at 3 Hertz. And on the right side, you see a parallel dynamic FEM analysis made on this pipe. And in the middle, you see the red sections with the highest movement. And this was correlated with the measurements result, and were leading to a computation and monitoring of the accumulated load factor of this pipe. On the next slide, please. With a proposal for a monitoring of this effect. In the right upper section diagram, you see here for a period of about 100 seconds, the impulses on this pipe, which were quite high as an acceleration spectrum. And in the lower right corner, you see this monitoring, this usage or the load monitoring by the system is called FAMOS-V, fatigue monitoring system for vibrations. And you see here that it is a kind of accumulated counting And also you see a prediction in the future, after which is an example of how many weeks the usage factor will be reached. And this is, as I said, a kind of online monitoring. On the left, you see the declaration on this. A real-time assessment on the remaining lifetime is possible. Vibration-induced fatigue assessment based only on a few acceleration measurements. So it means a few installed sensors, sometimes already available. In general, a digital twin has to be made for the structure, but that is possible. It's coming from the FEM. A reconstruction of complete stress history is possible with the stress tensors at relevant locations. Fatigue analysis, including a rainflow counting, as we saw, is possible on the cumulative usage factor, and the determination of remaining life duration via this integrated hardware and software is possible by this means. So the next slide is dealing with this concept we already implemented in the Swiss plant we mentioned. You see on the left side the AMUs, acquisition monitoring units, which are typically installed on a component or a system, which are gathering also together vibration signals and operational signals with this SCADA or PLCs, and combine them together already in the acquisition unit. You can have several acquisition units, and they bring their information to a central DBU database unit, which collects this data and makes possible as a server the further analysis, vibration analysis, electric analysis, fatigue analysis, performance analysis, and so on, and what you want. And in the end, on the right side, you can have a diagnostic prediction, manual diagnostic by experts, semi-automatic diagnostics by expert, or full diagnostic with expert-driven systems. So what is new with the system? I already mentioned that is a combination of vibrational data with the operational data already existing from the plant. And this they have they get a common time information that they can be correlated in the post analysis on any item. And this was implemented quite successful, and that is our idea. I think we should, which can be are very good for implementation of also secondary side vibrational issues. So coming slowly to the end on the next slide. Would be number 20. Number 20 will give an overview on the results and takeaway. Yeah, we have it. So we saw in the interviews of these, as I said, more than 12 plants, a comprehensive experience with flexible operation in Germany. Significant vibration impacts were observed on various components like nozzle, heat exchangers, pump height drives, valves, turbines, and so on in flexible operation, but they are plant specific. Impact in electrical components on the auxiliary system were low, but impact on the main generator, depending on local grid conditions, can be quite high. No indications on German plants that flexible operation has a negative effect on fuel vibrations. Proven countermeasures are already that the limitation of the power plant operation to uncritical power regions, typically 50, 60% to 100%, so not lower. Intense analysis on transient affected components and combined monitoring of operational and operational data in a central system. Impact and fatigue management measures necessary, implementation of monitoring, surveillance, and so on. Management of both thermomechanical and operational fatigue. So the main conclusion, plant by plant evaluation together with lessons learned from the power plants allowed German NPPs to develop operation envelope with minimal impact on vibrations. Monitoring and maintenance concepts were adapted to such a flexibility flexibility and allow a safe, reliable, flexible operation. That is the current outcome of these interviews. And then the last slide, informational slide. We see here some future ideas which could be dealt in the future with these items. So a more deep and comprehensive vibration data analysis on the impacted components can be made further. So also a surveillance concept on this component on primary secondary circuit could be established. So a completion with already existing projects like DIAM with our CADI software could be held with this in future terms. Vibrational fatigue monitoring to all kind of vibration in industrial structures, piping, valves, whatever you see. Online monitoring with digital twins is state of the art today. Also could be an item, very high cycle fatigue management, because it's a quite complex damage accumulation situation, especially of reactor internals, and special sensitivity of materials to very high cycle fatigue. And last but not least, in case of vibration of the main generator, there could be further measurements and analysis with empiric mathematical model taken into account. So on the last slide from my side and the next, we would like to thank our customers, the Preußen Elektra, the Energie Baden-Württemberg, the RBE in Germany, the Alpic in Switzerland. And so I thank you for your listening today.
Thank you very much, Tatiana and Peter, for this very interesting presentation, showing real results from actually how the power and will be influenced on the plant all the way down to measuring and doing analysis to show the impact on the usage factor and the fatigue. So it's, yeah, thank you for that presentation. I can also mention that this work that Framatome has been doing will, of course, result in a report which will be available on the Energy Forsk homepage. So please look for that. Perhaps we can send out information on that, Monica, when it's ready for to be able to download. We can send it out to the who has been participating to the seminar today. So thank you very much. I think we have time for one question. Otherwise, then we will continue with the discussion in the breakout session. But if there is anyone who have one question, I think we can have that in this room. Do you have anything, Monica?
Yes, I had a question for Peter, and I would like to really thank you for this very comprehensive table. I really love these kind of tables where you have everything very nicely structured. And I was wondering, looking at some of these measures that are taken, like changing blades or increasing maintenance, have they analyzed the extra cost for this compared to what it would be with like normal baseload operation? I mean, I know there are many different reasons for carrying out load follow. I mean, sometimes it's something to do with the plant, sometimes it's something to do with the grid, sometimes, yeah, as Tatiana mentioned. But if you have a choice, if you want to do load follow or not, I mean, you need to look into what would I gain in economical terms and what is the extra cost in increased maintenance.
Yeah, I'm sure that they dealt with the costs. I must say this was not the main focus for these interviews. It was a side effect, and from my impression, some events occurred which were not really foreseen, and I would say that this cost influence was put in post-analysis on this item, which is it worth to deal with this load follow or not. I think that is very operator specific, owner specific, on this item, yeah, it was taken into consideration, but I think that would overstep the range of this report if we would have also written it here.
I was just thinking if somebody mentioned it in the interview.
Yeah, I think I can add a few words to that. So the position of the NPPs, I mean, I asked this question many times, as you know. So they say that overall, of course, it has to be clear that there is a cost for flexibility, and this cost depends on which kind of flexible operation you perform. So they always analyze pros and cons, and they don't do it only once in the starting. So they also do it continuously, because also the pricing are changing. For example, sometimes they see that to provide more flexibility, you have to do much more things on your plant, and the prices are not high enough to do that. From one day to another, okay, I move from this gradient to another one, off to the ramp rate. I reduce the ramp rate, for example, because it's better for me. So it's a continuous process. But overall, the answer is that it was really valuable for German plants. So they will not do it if it will not be. So it had made sense last 20 years in the way how they performed, and they adapted that to their situation.